All right, my amazing students, we're going to be diving into Unit 6, and a good chunk of what we're about to talk about is review that you've seen in general chemistry or honors chemistry, but it's been a minute, so we need to talk through that. And that's what we're going to have going on right here. So today, we're going to be talking about 6.1, 6.2, and 6.3. And this is not new info. This is stuff that you saw in Gen Chem or Honors Chem. And then I'm also going to be talking to you about 6.6, and this is a little bit new, but honestly not too bad, and it just ties right into stoichiometry. So let's dive in. Turn to page 6. Okay, make sure you are following along and taking notes. And when I check this off to see if you have been watching the videos before class, I'm also going to be checking notes. So make sure you are following along and you're writing stuff down. Okay, so endothermic versus exothermic. And so what's going on with this energy? Is it like reactants higher, products higher? Where is the energy coming from? And so I've drawn this diagram for you before, but let's do this again. So this is the system, and the system is whatever we define it to be. So it might be a chemical reaction. It might be an ice cube that's going to melt. Like, we as the researchers, as the scientists, we define what the system is. But the more defined and simple the system, the easier it is to track this change in energy. So if we have our starting item, and let's just make it a chemical reaction for now. So we have our reactant atoms, and they're going to turn into products. Endothermic is gaining energy. So that means that we started with lower energy, and then it's going to increase in energy. So we're going to have higher energy. So if we're going from lower energy to higher energy, where did the energy come from? Like I said, this box, this is the system. Okay, system. And then everything else is the surroundings. Okay, like quite literally everything else. If the system is specifically these atoms that are going to react and turn into products, everything that is not those atoms, including you, including me, including the beaker, including the water molecules that are around it that didn't react, all of those things are part of the surroundings. And so surroundings are everything around it. Now, one of these items that is really common to be in the surroundings is a temperature probe. So let's going to put that, where should we put our temperature probe? Down here? Okay, so this is in the surroundings, and that's our temperature probe. And it's going to measure an increase or a decrease in temperature or energy. And just a reminder, the faster the atoms and the molecules are moving, the higher the temperature, and the lower the temperature. So we are going from lower energy to higher energy, and so energy is going to be leaving the surroundings and going to be entering the system. So energy leaves the surroundings and enters the system. Okay, so energy is leaving the surroundings, it is entering the system. And notice that the system is increasing in energy, but what does that mean for the surroundings? Okay, so if the system increases in energy, that means that the surroundings, they're going to decrease in energy. So if energy is leaving the surroundings, it's decreasing, and the temperature probe is part of those surroundings, what we would read is a lowering of temperature. So we would have a decrease in temperature. Okay, so if I have a chemical reaction going and I put a thermometer in there and the thermometer is showing me that we are decreasing in temperature, then this is endothermic. And the reason why it's decreasing in temperature is because energy is leaving the surroundings, which includes the temperature probe, and it's entering the system. Exothermic is the exact opposite of this. So when it's exothermic, again, I'm going to be checking, I want to be seeing all of these notes during class that they're already done. Okay, reactants turning into products. And this time, instead of reactants being lower energy and products being higher, it's the opposite. So we have a higher energy reactant and a lower energy product. And it's like, okay, great, we went from higher energy to lower energy, but where did that energy go? Well, it left the system. So energy leaves the system and it goes to the surroundings. Okay, so this is our energy. And what is part of our surroundings? The temperature probe. Okay, so energy leaves the system and enters the surroundings, opposite from before. So energy leaves the system and enters the surroundings. Okay, now that means that the system is going to be decreasing in energy. That makes sense because we went from higher to lower, and the surroundings is going to increase in energy. And if energy is being released, if energy is being gained by the system, the surroundings, which includes the temperature probe, then we would see an increase in temperature. Alrighty. A temperature probe that you might not have thought of, it's your hand. Like if we pick up a beaker and it feels cold to the touch, your hand is part of the surroundings, and energy is being taken away from your hand into the system, and that would be endothermic. Okay? But if you pick up a beaker that has a reaction going on in it and the beaker is hot, that's because energy is leaving the system and entering the surroundings, your hand being part of the surroundings, and so we see that increase in temperature. Alrighty. We've seen these energy diagrams before, so just a quick reminder about that. When reactants have lower energy and products have higher energy, that means we had to go from a lower to a higher energy. This is endothermic. Another way to say energy is enthalpy, and the symbol for enthalpy is delta H. So my total change in energy or change in enthalpy, when it is endothermic, it's a positive because we're gaining energy, because we're talking about the system right now, not the surroundings. The system had a positive change in enthalpy. It increased in the amount of energy. The opposite is true when it's exothermic. When it's exothermic, the reactants are higher energy, the products are lower energy. And so in order to go from reactants to products, we are decreasing our energy. So the total change in enthalpy or energy would be negative because it's energy that's lost. And where is it lost to? the surroundings. This also works for phase changes, so let's talk about that really quick. What if I go from a solid, okay, so new system, here we go. So I'm going to go from a solid to a liquid. And we know what that is. That's melting, going from a solid to a liquid. Reminder, solids, the atoms are close together and they're not moving very much. In a liquid, they're sliding past each other. So we have more energy in a liquid and less in a solid. And then gases are flying around the container, so their kinetic energy is very high. So we have low energy for a solid, moderate for a liquid, high energy for a gas. So if I'm going from a solid to a liquid, this is lower energy, and the liquid is higher energy. And in order to go from low to high, we need to gain energy. Energy needs to enter the system. Oh, by the way, that's one way I've had students in the past remember endothermic. So endothermic, because energy is entering, where exothermic energy is exiting. So energy is going to enter the system. Okay, well, what if this is solid water, an ice cube that we're talking about, and it's going to melt? And in addition to this, I'm going to hold this ice cube in my hand. Okay, so I have my system, which is the molecules that are making up this ice cube, and I got my hand out here, and it's part of the surroundings. Energy is going to leave my hand and going to enter the system. Okay, and we see that it'd be endothermic. That's why it feels cool to the touch, because energy is leaving my hand. The molecules, the atoms in my hand are actually slowing down because the energy from the atoms and molecules in my hand are being transferred to the system and speeding these molecules and atoms up. So for the ice cube, if the ice cube is the system, it's endothermic. But what if my hand was the system? What if all of a sudden we're talking about my hand being the system, not the ice cube? Then for my hand, it would be exothermic. Okay, this would be an endothermic exchange of energy for the ice cube, but if we're talking about my hand as the system, it's losing energy, and energy is being released to the surroundings, part of which is the ice cube, and that would be exothermic. So whenever we have a phase change, these energy exchanges go hand in hand. One item would be endothermic and another could be exothermic. So same like if we think about melting right now, we just talked about that. We said melting is endothermic, where freezing must be the opposite. It must be exothermic. Same, vaporization would be endothermic, and condensation would be exothermic. Now, think about this for a second. You know how they say evaporation is a cooling effect? Like if you go running, you start sweating, and that's your body trying to cool itself down because the water in your sweat is evaporating off of you. That's what we're talking about right now. Look, this vaporization, this sweat that was going from a liquid to a gas, it's endothermic. It's going to take energy away from you because you are part of the surroundings, and so it's going to cool you down. Okay. How is this exchange done? And it's through a transfer of heat, and it goes back to collisions yet again, that when a higher energy gas that's moving at a faster kinetic energy at a faster speed runs into a gas that has a lower energy, that it transfers that energy, that part of that kinetic energy is transferred, and that's going to make this increase in temperature and that one decrease if they run into each other. I have a demo that I'm going to be showing you in class that I think is a really cool way of seeing what's going on here. And so I'm put a little box for class, demo. So there's going to be a demo that we're going to do, and I'll have you jot some ideas down. All right, so this is going to be one of the big ideas that we're going to cover in class because it's so much easier when you can actually see this, and the demonstration does a good job of that. But the idea here is if we look at two items or two systems, and one starts with a lower average kinetic energy, and that's what we see, the temperature being lower, and then one has a higher average kinetic energy. When items from each system run into each other, some of this energy will be transferred to this guy. So it's going to lose energy here and gain energy there. Okay? And that will cause this colder, lower energy system to increase in kinetic energy, and it's going to cause the higher energy system to decrease in energy. Okay? And what's cool is this back and forth is going to happen until they equalize, till they reach thermal equilibrium. Thermal equilibrium. Okay? So that's what's going to happen. They're going to keep running into each other, transferring energy until we get the same average kinetic energy. One point that I want to highlight, though, that we've talked about before, the one falsehood about this model, this diagram, is it's showing that all of the arrows are the same size, and we know that's not true. It's just on average they're going to be the same size, where on average we're going to have larger vector velocity arrows and smaller. So if you want to make this a little more accurate, you can extend some of those arrows and you could like make some of them smaller, but on average they would be the same as the average over there. Okay, I want to save this example for class because again I really want you to be able to see it, so we'll come back to that. All right, this leads us to the new stuff, topic 6.6. Introduction to enthalpy of reaction. So when this reaction happens, when 4 moles of iron react with 3 moles of O2 and 2 moles of iron oxide is produced, this much kinetic energy is released, and I know it's released because of the negative. Okay, released. It's exothermic, it's exiting. And a way of thinking about that is as a product. It's like we made that energy, like that it was released out of the system. And so when we have an exothermic reaction and that change in energy is negative, you would put it on the product side, and then I wouldn't take the negative sign with it. The negative sign just means that it was released. So plus 1,651 kilojoules. Okay, so for every 4 moles of iron that reacts, that's how much energy is released. Or for every 3 moles of oxygen that reacts, that's how much is released. Or for every 2 moles of iron oxide that's produced, that's how much energy is released. Now on to our next one, we have a positive. So that means it's going to be not released but gained or absorbed. So think of it as a reactant instead of a product. In order for 1 mole of this ammonium nitrate to react and form these ammonium and nitrate ions, to break this apart, it's got to gain energy. And so this won't happen unless it absorbs or gains 27 kilojoules of energy on the reactant side. What's cool is now that we've added them into our balanced chemical reaction, we can actually do some stoichiometry with this. where we can say, hey, 4 moles will result in this, or 3 moles will result in that. So I'll show you an example here in a moment. Example number 1. Is the reaction exothermic or endothermic? It's exothermic. And I know this because I have a negative delta H. Okay, so that means it's going to be released. So let's write that in. We're going to do a product plus 92.2 kilojoules. That's how much is going to be released. What are the mole kilojoule conversion factors for each substance? So I'm not going to write this one down. I just want to talk you through this. If 1 mole of N2 is consumed, then 92.2 kilojoules of energy is released. That's one of these conversion factors. Here's another one. If 3 moles of H2 are consumed, then 92.2 kilojoules are released. Or if 2 moles of NH3 are produced, then 92.2 kilojoules are released. So we're going to use these conversion factors. How many kilojoules are needed to react with 50 grams of NH3? Okay, so we're starting with grams of NH3, and per usual, our connector is moles. So if I know grams of NH3, I want to go to moles of NH3. And then what's really cool is once I in moles of NH3, now I can convert it to kilojoules. So I have a 2-step goalpost. Grams of NH3. Again, I'm going to be checking your notes, and I want to see that you're following along and writing your notes as we go. To moles of NH3 to kilojoules. Okay? And we're starting with 50 grams of NH3. All right, I'm going to go grab a periodic table because I see moles over grams or grams over moles, and that's going to be molar mass. Okay, I've also got a calculator. So, N nitrogen, H hydrogen, but 3 of those. So I have 1 nitrogen, 14.01, plus 3 hydrogens, 1.008 times by 3. So my molar mass is 17.034 grams per mole. Okay, now I have kilojoules per mole, and this actually is my balanced equation. I know that there's going to be 92.2 kilojoules that are released for every 2 moles of NH3 produced. Alright, here's the top of my goalpost. 50 times by 92.2 divided by this 17 number times by 2. So, final answer, sig figs, 3 sig figs. So I get 135 kilojoules. That's how many kilojoules are needed. And really, that's almost not the right phrasing. That's how many kilojoules are released when this reaction happens. Okay, we are going to do one more example, and then we'll leave the last 2 for class. Alrighty, so an endothermic one. So I'm going to put the 180 kilojoules on the reactant side. It's endothermic. I know this because it's a positive delta H. What are the mole kilojoule conversion factors for each substance? Again, I'm not going to write this one down. I just want to talk through it with you. So, in order for 1 mole of N2 to react, it requires 180 kilojoules. Okay, that like without this, the reaction's not going to happen. So we need to absorb 180 kilojoules for 1 mole of N2 to react. Same thing, I'd have to absorb 180 kilojoules for the 1 mole of O2 as well. And 180 is absorbed in order to produce 2 moles of nitrogen monoxide. So my question is, how many kilojoules are needed to react when we got 50 grams again, but this time it's nitrogen monoxide is formed. Great. We're going from grams of nitrogen monoxide to moles of nitrogen monoxide to kilojoules. Grams of NO to moles of NO to kilojoules. We're starting with 50 grams. Grams over moles, molar mass, or moles over grams. 1 nitrogen and 1 oxygen. So 14.01 plus 16.00. And we are getting 30.01 grams per mole, and then we have 180 kilojoules that are consumed. 180 kilojoules are consumed to produce 2 moles of nitrogen monoxide. All right, I'm going to plug this in. So parentheses 50 grams times by 1 times by 180 divided by the 30 number times by 2. Oh, I need a parentheses. 30 number times by 2. Okay, we have 3 sig figs again, so I'm going to round this up. So it's 149.9. So for 3 sig figs, it'd be 150. But if I don't put the decimal, that's 2 significant figures. Trailing zeros are significant if there's a decimal, so that would be 3 sig figs. So 150 kilojoules would be consumed. All right. Everyone, well done. Lots of topics, but a lot of review, and we're definitely going to be going over topic 6.3 in more detail during class, and then we'll wrap up by doing example number 3 and number 4 together in class. All right, see you all then.